You mark down. It is quiet. The stars are out. The sky is not the only thing that is dark. A small rover no bigger than a book sits in a charging bay, waiting for the night to come. It is not a rover in the sense of adventure or exploration. It is a machine built to move through a world it has not seen, to find its way without knowing where it is. Tonight, it will leave. Not with a roar, not with a fanfare, but with the quiet certainty that it is about to begin. It is not the first time it has left. It is not the first time it has returned. But tonight, it will follow a path it has never walked before. And as it does, it will carry with it the quiet, methodical logic of how AI finds its way. It will not think in human terms. It will not question. It will not remember. It will only follow the logic of movement, of data, of uncertainty and resolution. So let us follow it, not with excitement, not with hope, but with the calm precision of someone who knows that the journey is more interesting than the destination. 1. The question, where am I? The rover begins its journey with a simple question. Where am I? This is not a question in the human sense. It is not a reflection on identity or place. It is a question of data, of position, of coordinates. It has been given a starting point. It has a map. It has a plan, but it does not know where it is. Coordinates alone are not enough. Coordinates are like a number on a page. They tell you where you are in a system of reference, but they do not tell you where you are in the world. Coordinates are a language, yes, but they are not the world itself. They are a way to describe it, not to live in it. Think of coordinates as a grid. You can say, I am at position 10, 20 asterisk, but that does not mean you know what is at 10, 20. You do not know if there is a wall, a hill, a river, or a road. You do not know if the grid itself is accurate or if it has shifted over time. Coordinates are useful, but they are not enough. They are a starting point, not a destination. So the rover must do more than just know where it is. It must know where it is in relation to the world it is moving through. And that is where the question, where am I, becomes a problem that must be solved. 2. Sensors. Cameras, lidar, radar, wheel encoders, inertial measurement, GPS. To answer the question, where am I? The rover uses a collection of sensors. Each one is a tool, a piece of the puzzle, but none of them on their own is enough. Cameras are the eyes of the rover. They take in the world, capturing images that can be analyzed for shapes, colors, and patterns. But cameras are not perfect. They can be blurry. They can be affected by light and shadow, and they can be deceived by reflections. A camera sees what is there, but it does not always know what it sees. Lidar is the rover's laser eye. It shoots thousands of beams at the world, measuring how long it takes for them to return. This creates a 3D map of the environment. LiDAR is precise, but it is also limited. It is expensive. It is not always available, and it can struggle in environments with a lot of reflective surfaces or smoke. Radar is the rover's sense of distance. It uses radio waves to detect objects, even in the dark. Radar is useful for detecting movement and speed, but it is not as detailed as LiDAR or cameras. It is not good at distinguishing between objects of the same size and shape. Wheel encoders are simple. They measure how far the wheels have turned, giving an idea of how far the rover has moved. But wheel encoders are not reliable. They can slip, they can be affected by terrain, and they can drift over time. A wheel encoder tells you how far you have moved, but not where you are. Inertial measurement units (IMUs) are the rover's internal compass. They measure acceleration and rotation, allowing the rover to estimate its movement. IMUs are useful for short distances, but they are not accurate over long periods. They can drift, and they can be affected by external forces. GPS is the global positioning system. It gives the rover a sense of its location on the planet. But GPS is not always precise. It can be affected by buildings, trees, and weather. It is a global reference, but it is not local. It is a starting point, not a final answer. Each of these sensors is a piece of the puzzle. None of them is enough on its own. Together, they form a collection of data. But data is not knowledge. It is the first step in understanding where the rover is. 3. Localization through landmarks, visual odometry, drift, and probabilistic belief. With data from its sensors, the rover begins to piece together its position. It looks for landmarks, things it has seen before. These are not just points on a map. They are features of the world, shapes and patterns that the rover can recognize. Visual odometry is the rover's way of tracking its own movement. It uses the images from its cameras to estimate how far it has moved. It compares the current image with the previous one and calculates the change. This gives the rover a sense of how it has moved, even if it has no idea where it is. But this is not always accurate. The rover can drift. It can misinterpret the world, and over time, its estimate of where it is can become wrong. This is called drift. It is a problem of uncertainty. The rover knows where it is based on its own movement, but it does not know where that movement has taken it in relation to the world. To deal with this, the rover uses probabilistic belief. It does not know where it is with certainty. Instead, it keeps track of the likelihood that it is in a certain place. This is not a guarantee. It is a probability. The rover maintains a set of possible positions and updates them as it gathers more data. This is not a simple question of coordinates. It is a question of confidence. The rover must believe in its position, but it must also be ready to change its mind if the data suggests otherwise. 4. Simultaneous localization and mapping, keyframes, loop closure, and ORB-SLAM. To solve the problem of where it is, the rover uses a technique called simultaneous localization and mapping, or SLAM. SLAM is the process of building a map of the world while simultaneously determining the rover's position within that map. It is a kind of puzzle where the rover is both the solver and the solution. SLAM works by using keyframes. These are specific moments in time when the rover captures important data. A keyframe is not just a point in time. It is a snapshot of the world, a collection of features that the rover can recognize and use to build a map. Loop closure is a critical part of SLAM. It is the moment when the rover recognizes that it has returned to a place it has already been. This is not just a simple recognition. It is a way to correct for drift. If the rover has wandered too far, loop closure allows it to realign itself with the map it has built. ORB-SLAM is a specific implementation of SLAM. It uses orb-oriented fast and rotated brief features, which are a type of visual feature that can be extracted from images. ORB-SLAM is a real-time system, meaning it can process data as it comes in, without waiting. It is used in many applications, from drones to robots. It is not the only method, but it is a powerful one. Not all robots use ORB-SLAM. Some use different methods, such as visual SLAM, lidar-based SLAM, or even combinations of different techniques. But the principle is the same. The rover must build a map of the world while figuring out where it is in that world. This is not a simple task. It is a complex interplay of data, movement, and uncertainty. But it is the foundation of how the rover finds its way. 5. Maps as layers. Geometry, semantics, lanes, traversability, and changing conditions. Once the rover has built a map, it does not just use it as a static representation of the world. It uses it as a dynamic, layered system. A map is not just a grid of coordinates. It is a collection of information, each layer telling a different story. Geometry is the first layer. It is the shape of the world, the positions of objects, the distances between them. Geometry is the structure of the world, the foundation upon which everything else is built. Semantics is the second layer. It is the meaning of the world. A road is not just a line on a map. It is a path that can be traveled. A stop sign is not just a shape. It is a rule that tells the rover what it can and cannot do. Semantics adds context to the geometry. Lanes are a form of semantics. They are not just lines on the road. They are boundaries, they are rules, they are the structure of movement. A lane is not just a place to drive. It is a way to navigate, a guide for the rover to follow. Traversability is the third layer. It is the ability to move through a space. A surface may be flat, but it may not be safe to drive on. A surface may be smooth, but it may be too wet or too uneven. Traversability is a question of risk and possibility. It is not just about where the rover is, but about where it can go. Changing conditions are the final layer. The world is not static, it changes with time. A road may be closed, a traffic light may change, a pedestrian may step into the path. These are not just events. They are changes that the rover must account for. The map is not just a snapshot of the world. It is a living, evolving representation. These layers are not separate, they are interconnected. Geometry provides the structure. Semantics gives meaning. Lanes define movement. Traversability determines safety. Changing conditions require adaptation. Together, they form the basis of how the rover navigates the world. 6. Route planning from Dijkstra to A-star. Explaining cost so far plus a heuristic estimate in plain English. With a map in place, the rover must decide where to go. This is the problem of route planning. It is not just about finding the shortest path. It is about finding the best path, the one that is safe, efficient, and appropriate for the rover's mission. Dijkstra's algorithm is one of the earliest methods for finding the shortest path. It works by exploring all possible paths from the starting point, expanding outward until it reaches the destination. It is reliable, but it can be slow. It is like a spider spinning a web, checking every possible connection before finding the shortest thread. A-star is an improvement on Dijkstra's algorithm. It is more efficient. Instead of expanding all possible paths, A-star uses a heuristic estimate. The heuristic is a guess about how far the rover is from the destination. It is not perfect, but it is useful. A-star balances the cost so far, how much the rover has already traveled with the heuristic estimate, how much it still has to go. This allows the rover to find a path that is not just the shortest, but also the most efficient. The cost so far is the total distance the rover has already traveled. It is a measure of how much effort has been spent. The heuristic estimate is a guess about how much effort is still needed. Together, they form a way to evaluate the path. The rover chooses the path that minimizes the total cost. This is not a perfect system. Heuristics can be wrong. They can lead the rover down a path that is not the best, but they are a useful approximation. They allow the rover to make decisions without having to explore every possibility. So route planning is not just about finding the shortest path. It is about finding the best path, the one that balances cost, safety, and efficiency. It is a question of trade-offs, of choices, of uncertainty. 7. Predicting other moving agents. Multiple plausible futures, interaction, and uncertainty. As the rover moves through the world, it is not alone. Other agents are present. These can be vehicles, pedestrians, animals, or even the wind. Each of them is moving, and each of them has its own path and purpose. The rover must predict where these agents will go. This is not a simple task. Each agent has its own goals, its own behaviors, and its own uncertainties. The rover cannot know everything about them. It can only make educated guesses. Multiple plausible futures are possible. The rover cannot know with certainty where the other agents will go. It can only consider the most likely paths. This is where uncertainty comes in. The rover must account for the fact that the world is not deterministic. It is a system of probabilities. Interaction is another challenge. The rover must anticipate how other agents will respond to its movement. If it turns left, will a car stop? If it speeds up, will a pedestrian cross the road? These are not simple questions. They require the rover to consider the behavior of others, to predict their actions, and to adjust its own accordingly. This is not just a question of movement. It is a question of cooperation, of prediction, of understanding. The rover must navigate not just the physical world, but the world of other agents as well. Uncertainty is the key. The rover cannot eliminate it. It must work with it. It must find a way to move through a world that is not entirely known, not entirely predictable, but still navigable. 8. Converting a route into motion. Trajectory optimization, feedback control, replanning, and the contrast between modular and learned end-to-end systems. Once the rover has a route, it must convert that route into motion. This is not a simple task. A route is a plan, a set of directions. Motion is the actual movement through the world. The two are not the same. Trajectory optimization is the process of turning a route into a path that the rover can follow. It is not just about finding the shortest path. It is about finding the path that is safe, efficient, and possible. Trajectory optimization considers factors such like speed, acceleration, and the physical limitations of the rover. Feedback control is the system that ensures the rover follows the path. It is like a self-correcting mechanism. If the rover drifts off course, the control system adjusts its movement to bring it back. Feedback control is essential for maintaining accuracy and stability. Replanning is the process of adjusting the route when things change. If the rover encounters an obstacle, if the road is closed, if a new agent appears, the rover must reconsider its path. Replanning is not a one-time event. It is a continuous process, a way to adapt to the dynamic nature of the world. There are two main approaches to this problem: modular systems and learned end-to-end systems. Modular systems break the problem into smaller, manageable parts. Each part is handled by a different component. For example, one component handles navigation, another handles control, and another handles perception. These systems are reliable and well understood, but they can be complex and difficult to scale. Learned end-to-end systems, on the other hand, use machine learning to handle the entire process. They take in raw data from the sensors and output a path or a set of movements. These systems can be more efficient and adaptable, but they are also harder to debug and understand. They are not always transparent, and they can be sensitive to changes in the input data. Both approaches have their strengths and weaknesses. Neither is perfect. The choice between them depends on the specific requirements of the task, the environment, and the available data. Quiet interlude, the map that never stays still. The rover moves, and with it, the map shifts. It is not a static image, not a grid of coordinates frozen in time. The world it traverses is constantly changing, and so must the map. This is not a matter of design, but of necessity. Every moment, the rover gathers new data. Surfaces that were once smooth now show cracks. Obstacles that were invisible now cast shadows, and paths that were clear now bend around unexpected turns. The map, therefore, is not a record of the world as it was, but a living reflection of the world as it is. This dynamic nature of the map is not a flaw, but a feature of navigation itself. The rover does not merely follow a predefined route. It must continuously update its understanding of the environment. This is where the interplay between perception and planning becomes most evident. The rover's sensors feed in a stream of information, and from that, the system must infer the current state of the world. It must distinguish between static objects and moving agents, between safe terrain and hazardous ground, and between paths that are open and those that are blocked. The map, then, is a representation of probability. It is not a perfect mirror of reality, but a best guess based on available data and historical patterns. The rover must account for uncertainty in every decision it makes. When a new object appears in its path, the map must quickly reevaluate the surrounding area, recalculating the safest trajectory. When a road is closed, the map must find an alternative route, not by retracing steps, but by exploring new possibilities. This constant updating of the map is made possible by a delicate balance between different systems. The rover's perception module collects data. The planning module uses that data to generate a tentative path, and the control module ensures that the rover follows the path with precision. But these systems are not isolated. They are interdependent, and the map serves as the bridge between them. It is the point where the rover's understanding of the world converges with its ability to act upon that understanding. In this way, the map becomes more than a tool for navigation. It becomes a symbol of the rover's adaptability, its willingness to learn, and its capacity to respond to an ever-changing environment. It is not a fixed plan, but a flexible guide, one that evolves as the rover moves through the world. It is a testament to the complexity of navigation, not just the act of moving from one place to another, but the continuous process of understanding, adjusting, and improving. And so, as the rover continues its journey, the map shifts once more. It is not a static image, but a living document of the world in motion. It is a reminder that navigation is not about certainty, but about the ability to navigate uncertainty. It is a quiet interlude in the story of the rover, a moment of reflection on the nature of movement, perception, and the ever-changing landscape of the unknown. In the quiet hours of the night, when the world is still and the sky holds its breath, the systems that guide us through the dark continue their silent work. Navigation, in its most fundamental form, is not a single act but a continuous interplay of many subtle and often unseen processes. When GPS signals vanish, whether due to signal blockage, interference, or the simple absence of a satellite overhead, autonomous systems must rely on other means to remain oriented. This is not a sudden shift, but a gradual transition into a different mode of knowing, one that is grounded in the physical world rather than the vast and sometimes unreliable sky. At the heart of this transition is the concept of inertial drift. Without the steady reference of GPS, the system turns to inertial measurement units, which track acceleration and orientation using gyroscopes and accelerometers. These sensors provide a continuous stream of data about motion, but they are not perfect. Over time, small errors accumulate and the system begins to drift. This is not a failure, but an inevitable consequence of the physical world. The drift is like a whisper in the wind, a gentle but persistent deviation that must be accounted for. To counteract this drift, the system turns to another method: wheel slip. By measuring the rotation of the wheels and comparing it to the actual movement across the ground, the system can detect discrepancies. If the wheels rotate less than expected, it may indicate that the vehicle is slipping on a surface, or conversely, that it is moving more than the wheels suggest. This information helps refine the estimate of position and orientation, offering a second layer of correction. But even with these methods, the system remains uncertain. It is in this uncertainty that visual landmarks become crucial. Cameras scan the environment, identifying familiar shapes, textures, and patterns. These landmarks are like old friends in a familiar neighborhood, offering a sense of place and direction. However, the system does not simply match a single image to a known location. It builds a probabilistic model of the surroundings, weighing the likelihood of each feature being where it is expected. This is not a certainty, but a confidence, a measure of how likely the system is to be right. Relocalization is the process by which the system recalibrates itself when it loses track. It may have wandered too far from known landmarks, or it may have encountered an unexpected obstacle or change in the environment. At this point, the system searches for familiar features in the new surroundings, gradually piecing together a new understanding. This is not a sudden snap back to a previous position, but a slow and careful reconstruction of where it is. Loop closure is the moment when the system recognizes that it has returned to a place it has seen before. This is a critical point in the navigation process, as it allows the system to correct for accumulated errors. The system compares its current perception with past observations, and if they match, it can adjust its internal model of the world. This is a quiet but powerful act of self-correction, a way of ensuring that the system does not drift too far from the truth. Yet, even with all these methods, the system does not know exactly where it is. Instead, it maintains a probability distribution that represents the likelihood of its position across a range of possible locations. This distribution is more honest than a single coordinate because it acknowledges the uncertainty inherent in the process. It does not claim to know precisely where it is, but it does know where it might be and how likely each possibility is. This is the nature of navigation in the absence of GPS, not a precise answer, but a measured and thoughtful approximation. In the end, the system continues its journey, guided by a quiet and steady set of assumptions, corrections, and probabilities. It moves through the dark, not with certainty, but with understanding. The world is not a place of absolute coordinates, but a space of probabilities, where each step is a balance of knowledge and guesswork. And in this balance, the system finds its way. The night is quiet, and the road stretches forward in a long, unbroken line. In this stillness, the machine moves with a purpose that is neither urgent nor slow. It is guided by a set of rules, a series of calculations that unfold in the dark, shaping the path ahead with a precision that is both mechanical and methodical. This is the nature of autonomous navigation, a continuous interplay of possibilities, a balance between the known and the unknown. The machine does not simply follow a route. It considers the road as a complex web of interactions, where each turn, each intersection and each merging point introduces new variables. At a merge, for instance, the machine must anticipate the movements of other vehicles, each of which may have its own trajectory, its own set of intentions. There is no single correct path forward, only a range of plausible futures, each one unfolding with a different probability. The machine does not choose. It evaluates and it adapts. Uncertainty is a constant companion. The machine does not know exactly what will happen in the next few seconds, nor does it need to. It operates within a margin of conservatism, favoring paths that are safe and predictable over those that are uncertain. This is not hesitation, but a calculated approach. It is the machine's way of ensuring that it remains within the bounds of acceptable risk, even as the world around it changes. Replanning is a necessary part of this process. The machine does not rely on a static plan. Instead, it continually reassesses its surroundings, recalculating its path with each new piece of information. A sudden change in traffic, an unexpected obstacle, or a shift in the flow of vehicles all require adjustments. The machine does not panic. It simply recalibrates, ensuring that its movements remain aligned with the ever-changing environment. At crossings, where the paths of multiple entities intersect, the machine must navigate a delicate balance. It must predict the actions of others, not with certainty, but with a degree of confidence. It must decide when to yield, when to proceed, and when to wait. These decisions are not based on intuition, but on a vast array of data points, each one contributing to a more complete picture of what is happening in the moment. The machine does not move in isolation. It is part of a larger system, one that includes other vehicles, pedestrians, and environmental factors. Each of these elements influences the machine's path, and the machine, in turn, influences the path of others. This is the nature of autonomous navigation, a continuous exchange of information, a shared responsibility for the movement of all participants. In the quiet of the night, the machine moves with a rhythm that is both steady and fluid. It does not rush, nor does it linger. It follows a path that is shaped by the world around it, adapting to the needs of the moment without losing sight of its ultimate goal. There is no grand design, no overarching plan beyond the immediate steps that must be taken. Instead, there is a quiet persistence, a steady motion that carries the machine forward through the dark. The machine is not a visionary, nor is it a leader. It is a participant in a vast, interconnected system, one that is constantly evolving, constantly shifting. It does not seek to control the environment, but to navigate it with care and precision. In doing so, it ensures that its movement is both safe and efficient, that it contributes to the flow of traffic without disrupting it. As the night deepens, the machine continues its journey, a silent witness to the quiet rhythm of the road. It moves through the dark with a purpose that is neither loud nor dramatic, but steady and sure. It is a reminder that even in the most complex systems, there is order, and that movement, whether of people or vehicles, can be guided with care, with patience, and with a deep understanding of the world it traverses. The path begins as a sequence of points, a chain of coordinates etched into the mind of the system. These points are not arbitrary. They are the result of careful consideration, shaped by the environment, the goals, and the constraints of motion. As the system processes this plan, it transforms it from a static idea into a dynamic action. The first step is to convert this sequence into a continuous path, a smooth trajectory that the vehicle can follow. This trajectory is not just a line on a map. It is a series of curves and straight lines, each calculated to ensure the vehicle moves efficiently and safely through its surroundings. Once the trajectory is established, the system must translate it into commands that the vehicle can execute. Steering, speed, and acceleration are the elements that bring the plan to life. These commands are generated in real time, adjusting as the vehicle moves. The system continuously evaluates the current state of the vehicle and the environment, ensuring that the motion remains aligned with the original plan. This process is not static. It is a constant dialogue between the intended path and the actual movement. Feedback control is the mechanism through which this dialogue takes place. Sensors provide a stream of data about the vehicle's position, orientation, and speed. This data is compared to the expected values, and any deviations are corrected. The control system acts as a mediator, adjusting the commands to bring the vehicle back on track. This loop of sensing, comparing, and correcting is what allows the vehicle to navigate with precision, even in the face of unexpected obstacles or changes in the environment. The concept of the receding horizon is central to the system's ability to adapt. Instead of following a fixed path from start to finish, the system looks ahead, planning for the next few seconds rather than the entire route. This short-term focus allows it to respond to immediate conditions while still maintaining an overall sense of direction. The horizon shifts forward as the vehicle moves, ensuring that the system remains agile and responsive to new information. Safe stopping is another critical aspect of autonomous navigation. The system must be able to halt the vehicle at any time, whether due to an obstacle, a change in the environment, or a sudden command. This requires not only the ability to stop, but also the ability to do so in a controlled and predictable manner. The stopping distance, deceleration rate, and the vehicle's position relative to surrounding objects are all factors that the system must consider. This ensures that the vehicle can come to a complete stop without causing any harm or disruption. The distinction between modular planning and learned end-to-end policies reveals the depth of the system's design. Modular planning is a structured approach where each component of the navigation process is handled by a separate module. These modules work together, each responsible for a specific task, such as path planning, obstacle avoidance, or control execution. This method is transparent and easy to debug, allowing engineers to isolate and improve individual parts of the system. In contrast, learned end-to-end policies rely on a single model that learns to map raw sensor data directly to control commands. This model is trained on vast amounts of data, learning to recognize patterns and make decisions without the need for explicit planning steps. While this approach can be more efficient and adaptable, it lacks the transparency of modular systems, making it harder to understand or modify. Both approaches have their strengths and are often used in tandem. Modular planning provides stability and predictability, while learned policies offer flexibility and responsiveness. The balance between these two methods is what allows the system to navigate complex environments with both precision and adaptability. In the quiet of the night, as the vehicle moves along its path, the system operates in a continuous and seamless flow. It is not thinking, not planning, but rather executing a sequence of well-defined actions, guided by data, logic, and a deep understanding of the physical world. The motion is smooth, the commands precise, and the environment ever-changing. Yet, the system remains steady, moving forward with the quiet confidence of a machine that knows its way. 9. Failure, humility, and what it would mean for machines to navigate unfamiliar worlds. End softly.